Okay, in this particular screencast, I want to go over the math related to the solutions. One thing is to get a solution, another thing is to get a solution of a particular concentration. Now, there are various different ways that you could use to express your concentration, and some of those you might have seen in General Chemistry 1, the first one being molarity. This is the most common concentration, and oftentimes when you go to the lab and you have to work with the chemicals, we do express it in molarities, and higher the number, that basically tells you that there is greater amount of solute that is present. So for example, if you have a 1 molar HCl solution, that basically means that you have 1 mole of the solute, which is HCl in this case, and you have dissolved it in a liter of solution. Well, what does that mean? That means that you would have taken 1 plus 35.5 grams, that means 36.5 grams of HCl. You would put it in the beaker, and then you would continue to add distilled water till you hit the 1 liter mark. That means the total combined volume of the solute and the solvent happens to be a liter. Okay? Another unit that we often use is molality, and molality is the moles of solute per kilogram of solvent. So understand the difference between molality and molarity. In case of molarity, we are dealing with the liter of solution. So it's a combination, it's a combined volume between the solute and the solvent, whereas in molality, we explicitly would have taken, if I had to, let's say, generate a 1 molar HCl solution, I would get 36.5 grams of HCl. I would get 1 kilogram of water, which by the way you can take as 1 liter of water, because you know that the density of water is 1 kilogram per liter. So you can take 1 liter of water in a measuring cylinder or something and dump that in with the 36.5 grams. So if you think about the overall volume of this solution, it's going to be slightly higher than the volume in case of the molar solution. Okay? All right, let's think about mole fraction. Mole fraction is essentially the fraction of moles of a certain component. So if you have many things, let's say A, B, C, many things in a mixture, the fraction of moles for each of these should add up to 1. Okay, usually it's denoted by, I'm showing here as x, it's actually chi. So chi A plus chi B plus chi C, all of those should add up to 1 because it's a fraction. So moles of a certain component divided by the total number of moles, that will give you the mole fraction. If you multiply that by 100, that will be called as a mole percent, something we discussed. Both of these we discussed in the chapter on gases in Gen Chem 1. Okay, let's go forward. Another one that you might have encountered in the chapter on stoichiometry, also still used, not just in a theoretical sense, but used by goldsmiths. If they have to specify what percentage of a certain metal is present in a given alloy. So mass percent. Mass percent is the mass of component divided by the total mass of the solution times 100. And concept-wise, it's very similar to the ppm and the ppb. If instead of 100 you multiply it by 10 to the power of 6, we are going to call it ppm. If instead of 100 you multiply it by 10 to the power of 9, we would be referring to a parts per billion. But the latter two, these two, are used essentially more by environmental chemists to say how many parts per million or parts per billion of cadmium or lead, or one of those heavy metals which are bad for human beings, bad for their health, how much of those are present in the drinking water. So the question is, what is the mass percent concentration of a saline solution prepared by dissolving 1 mole of sodium chloride in 1 liter of water? The density is given to be 1.00 grams per milliliter. The molar mass is 58.443 grams per mole. So a couple things here. The first thing you should note is that it's a solution of NaCl, so that is your solute. And it's an aqueous solution. Since you're dissolving it in water, that becomes your solvent. So now if you go back to the definition of mass percent, that's nothing but mass of the component, mass of component, so component being the solute here, NaCl, because that's what we are trying to figure out, mass percent concentration of a saline solution, divided by total mass times 100, since it's a mass percent. So basically, if you knew the mass of sodium chloride in the system, and if you knew the mass of water, because you will need both of those to determine the total mass, realize that both solute plus solvent give you the solution. So let's go for that. I have been given some information. So I have been given that I'm supposed to deal with 1.00 moles of sodium chloride. And I'm also given that the molar mass of sodium chloride is 58.443 grams per mole. So hopefully you can see, using dimensional analysis method, I can convert the moles given into the grams. So I have 58.443 grams of NaCl. And I just have to find out the mass of water that I have, since we are given that we have 1.00 liter of water, and the density of water is 1 gram per milliliter. 1 gram per milliliter. I might be able to say, if I multiply and divide by 1,000, I might be able to say that I'm dealing with 1 kilogram of water, right? So 1 kilogram basically reflects 1,000 grams H2O. Let's now plug this data in, what we have just determined. Let's plug this into our original formula we were seeking. Let me just make some room. And so we are going to go with 58.443 divided by, denominator becomes 1,000 plus 58.443 times 100. So when you solve that, you're basically seeking 58.443 divided by 1058.443 times 100, which comes out to be 5.52%, and that is going to be your final answer. That is your mass percent for the saline solution chosen. Okay, the next question is, what is the molality of a solution prepared by dissolving 0.385 grams of cholesterol, the formula for which is C27H46O, in 40.0 grams of chloroform? What is the mole fraction of cholesterol in the solution? So we have to determine two things here. One is the molality. Let's perhaps switch the color. Molality, which, by the way, is defined as moles of solute divided by kilograms of solvent. So that's the first thing. And then the other thing we have to determine is the mole fraction, chi, for cholesterol. So this is being done for the solute. So we would say that our component is the solute, really. So we would say again, moles of solute, divided by total moles. total moles. So recall that since this is a solution between cholesterol and chloroform, you will need to determine, in order to determine the total moles, you need to determine the moles of cholesterol as well as moles of chloroform for the case of the mole fraction. Okay, so let's take each one one at a time. First things first, you are given 40 grams of chloroform, which is my solvent, and in order to convert that into kilograms, all you need to do is just divide it by 1,000, because you know that each gram is essentially 10 to the power of negative 3 kilograms. So 10 to the power of negative 3 kilograms makes 1 gram. So gram and gram cancels off, and you can say that the kilograms that you have is 0.04 kilograms of the solvent, which is chloroform, CHCl3. So all you have to determine now is the moles of solute. Just for the sake of simplicity, I want you to be able to use 12 for carbon, 1 for hydrogen, and 16 for oxygen. And so if you had to determine the molar mass, you would say 12 times 27 plus 46 times 1 plus 16 times 1, and that is going to give you the molar mass of cholesterol. If you work out the math, that should come out to be 386 grams per mole. So let's now try to determine the moles of solute. Moles of solute, those are going to be 0.385 divided by 386 grams per mole. So grams and grams cancel, and the answer is going to come out to be in moles. So let's work out that math. Should be close to 0.001, but I still want to go through the math. So 0.385 divided by 386 comes out to be 9.97 times 10 to the power of negative 4. So all you got to do now is plug in those numbers in the definition of molality. So that's the final step. The numerator is 9.97 times 10 to the power of negative 4 moles per kilogram of solvent. So we are going to divide it by 0.04 kilograms, and that's going to be my final answer. Comes out to be 0.0249, and since we have 3 significant figures in the data, I'm going to stick to all 3, and we are going to say this is going to be our moles per kilogram, or you can write that as a small m for molal solution. Let's take a quick look at the determination of chi. Of course, my numerator, we have determined what that number is going to be, 9.97 times 10 to the power of negative 4. Total number of moles. So if I can divide the grams of chloroform by the molar mass of chloroform by using 12 for carbon, 1 for hydrogen, and 3 times 35.5 for chlorine, I should be able to determine the overall number of moles. This comes out to be 119.5 grams per mole. And so if I had to divide 40 by 119.5, 40 divided by 119.5, that's close to a third, so it does come out to be 0.334. So we are going to just simply add 0.334 plus 0.000997, 0.000997. So that gives me a numerator and a denominator of 33572. Uh, and we are going to just plug in the numbers, get your final answer. 572. That gives me 0.00296. And again, those are three significant figures, so we are good. And just a checkpoint, realize that chi is a mole fraction. That means that number is always going to be less than 1. And this number is less than 1 as well, so we're good. Okay, let's discuss the next question. The question is the density at 20 degrees of a 0.258 molar solution of glucose in water is given to be 1.0173 grams per milliliter. Molar mass of glucose is 180 grams per mole. What is the molarity? So again, we should start by consolidating what we have been given and where we are at. What is it that we want to figure out? Since we are given 0.258 molar solution, I want to kind of define for myself what that is. Since molality is given as moles of solute divided by kilograms of solvent, and I'm supposed to assume that I have 1 kilogram of the solvent. So if this is 1 kilogram, then whatever is my value, 0.258 is the value that I have been given with. I can simply say that moles of solute would be 0.258 moles, since kilogram and kilogram is going to cancel off. So I can say times 1 kilogram, kilogram cancels, and 0.258 moles is the moles of glucose that I have. Now, if I have to determine molarity, so this is what I want to find out. I need the moles of my solute, and I need the liters of solution. I need the volume of the solution. Now, one thing that you again have to keep in mind is when you're thinking about a solution, it's a combination of solute plus the solvent. So far, we have the value of the numerator straight from here, but we will have to work out the liters of the solution that is provided. So, in order to determine that, we need to use the information that's given for the density of the solution. So the density has been given, the density of the solution has been given to be 1.0173 grams per milliliter. But what is density after all? The density can be written as mass of the solution divided by volume of the solution. And if you really think about it, it is this volume that I am after. Those are the liters of solution that I'm after, is the same thing. So one can say that if I can figure out what this mass of solution is all about, I should be able to determine the volume, plug that number in the formula, and get my answer. It's as simple as that. Let's take a look how we could get the mass of solution. Recall, I just said that a solution is a combination of solute and solvent. That means mass of the solution is also going to be a combination of mass of solute plus mass of solvent. Mass of solvent is already assumed to be 1 kilogram, so I'm just going to write that as 1,000 grams. So if somehow I'm able to determine mass of solute, I'm in business. So now the question is there any piece of information that gives me mass of solute? And the answer to that is yes, absolutely. You are given, let me make some room here, perhaps. Okay, let's write that again. So since we have moles, which are nothing but mass over molar mass, and the moles are 0.258, I can say mass is going to be equal to moles times molar mass. So we will say 0.258 moles times 180.2 grams per mole. Mole and mole will cancel off, and you're going to end up with an answer in grams. So let's write that. Let's calculate. The number is coming out to be 258 times 180.2, 46.49 or 46.5 grams is what you get. So now I have the moles, the mass of the solute. The mass of solvent was 1000. So let's plug that value in. The mass of solution from here, mass of solution is going to be equal to 1000 plus 46.5, which would be 1046.5 grams. So I have the mass of the solution, I have the density of the solution. Can I calculate the volume? The answer is yes. Let's make some room here first. So let's again show our work. 1.0173 grams per milliliter times volume of the solution will give you 1046.5 grams. So one can say volume of the solution is going to be 1046. I'm going to divide both sides of the equation by 1.0173. So milliliter goes on top. The 1.0173 grams comes at the denominator. Grams and grams cancels off. And on my calculator, I am punching in 1046.5, and I'm going to divide that number by 1.0173. Comes out to be 1028.7, 1028.7 milliliters. So I'm going to just plug that number into my equation. Just make sure that it's entered as liters. So I must divide this number by 1000 before I plug in the number and determine molarity. And that's about it. So let's calculate that as well. Let's first make some room. So my numbers were 1028. My numbers were 1028.7 milliliters for the volume, and the moles were 0.258. So when you plug in the numbers of the moles and the volume, you are going to get your final answer in moles per liter, or you can write a simple capital M to show your final answer. So I'm punching in 287. Comes out to be 0.2508, and since my number of sig figs were essentially 3 in my data, in the original data, I'm going to report it as 0.251 molar solution. Realize this number is going to be lesser as compared to the number that you saw for the molality, because molality again is per kilogram of the solvent, molarity is per liter of solution. So you have an additional number in the volume, so of course your overall value, overall number is going to go down if your denominator is higher. Okay, this problem is just the opposite of what we just did. The density at 20 degrees Celsius of a 0.500 molar solution. So this number is a molarity value, which basically means again moles of solute per liter of solution. And that number has been given to be 0.500 molar. Okay, and the solution is what? It's acetic acid in water. So that's my solvent, and this is my solute. And the density is given. Okay, what is the concentration of this solution in molality? So I have to go from capital M to small m. That's what I'm supposed to be doing. The molar mass has been provided to be 60.05 grams per mole, and I have been told that I should assume 1 liter of solution. Well, let's start again the same way as we did in the previous question. What does 1 liter of solution basically mean? 1 liter would mean that the moles of solute is going to be 0.500 moles per liter times 1 liter. Liter cancels. So you basically have 0.500 moles of acetic acid. CH3COOH, that's acetic acid. Now, we have been given that the density, density is given to be 1.0042 grams per milliliter. This is density of what? This is the density of the solution of acetic acid in water. This is not pure water. This is the solution of acetic acid in water. So one can say that this also is going to be the mass of solution over volume of solution. So one can say that if I know the volume of solution, which by the way I'm supposed to essentially assume to be a liter, I should be able to determine the mass of the solution from here. So since this number, the denominator is 1 liter, I should be able to say that 1.0042 grams per milliliter times 1 liter should give me the mass of solution, basically multiplying both sides of the equation by the volume of the solution. And since the denominator is in milliliters, so you need to of course do that conversion. So I'm going to say 1.0042 times 1000 divided by 1000. We are just going to do that. So that will be grams. This will be milliliters. This is 1 liter. 1 liter. So 1 liter. This part, the 1000 milliliter, boils down to a liter. So those two are going to get cancelled. And so I can say safely that 1004.2 grams is essentially the total number of grams that we are dealing with as far as the mass of the solution goes. Now, realize you can represent this in terms of kilograms because overall in the end we would be seeking the kilograms of the solvent, and that would just be the dividing the number by 1000, so it will be 1.0042. Anyway, I'm supposed to calculate molality, and molality by definition is moles of solute per kilograms of solvent. We just determined the moles of solute a couple minutes ago, and that was because we had assumed the 1 liter of solution. We know that this is 0.500 moles. So if by some means I'm able to determine the kilograms of solvent, I'm in business. Just a couple minutes ago, I also determined that mass of the solution is 1004.2 grams, right? Now, solution, recall, is a combination of the solvent plus the solute. So that together right now I know is 1004.2. Now, if I know the moles of solute and I know the molar mass of the solute, hopefully you can envision that I can determine the mass of the solute. So 0.500 moles times 60.05, that comes out to be 30.025. This is grams per mole. Moles and moles cancelled off. So I have the mass of the solute as well. So can I say that the mass of solvent, basically subtracting mass of solute from both the sides of the equation, I would say 1004.2 grams minus 30.025 grams. That should give me the mass of the solvent. So this comes out to be 974.175 grams. And in kilograms, you can say we are going to divide this by 1,000. So it will be 0.974175. So plugging that value in, we would have molality as 0.500 divided by 0.974175, and let's see what the number comes out to be. Looks like it's gonna be 0.5 divided by 0.974175, 0.513 mole or moles per kilogram. And that makes sense because our value in molarity, the capital M was 0.500 molar. And I told you early on that the number that you get in molar terms always is slightly larger as compared to the number that you see in molar terms, because in case of molarity you have volume, which comprises of volume of both the solute as well as the solvent. All right, so that's the math part, and that's about it for in this video.